Hey, everybody. Happy Friday to you. Hopefully, your week has gone well. Um, Aside from the seniors who just found out that you've probably had your last class at Burnsville High School, actually in the physical building. Sorry to hear that for you guys. Not the way you probably envisioned this school year ending, but hopefully we can continue to learn some good stuff and have it be a productive end to the school year. And for us in this class right now, that's going to mean starting to take a look at some of the free response questions. Hopefully, you had a chance to take a look at questions number 1 and 3. If you haven't already, pause this right now. Go take a look at questions 1 and 3, and come back and join us in a few minutes. Question number 1 looks like this. We've got a region. You can't see the shading very well on this copy of it, but hopefully on your sheet you can see it, or on your PDF. We're told that R is the region bounded by these curves in the first quadrant. So that means x equals 0 is a boundary, and then bounded above by 1 minus x cubed, below by sine of x squared. Worth noting, this is a calculator necessary question. In fact, as I was writing down my work, I tried to minimize. This is all you need to write down in order to get credit for these types of questions. First, I said that I would need to figure out where these two functions are equal to each other, so I set them equal. And this is all you need to say. You don't have to say, I used my calculator. It's obvious that you had to use your calculator to do this. You don't have to tell them what buttons you pushed or what function you used. Solving an equation using your calculator is something that is just assumed that you're going to do. Now, I wrote down 5 decimal places here. I also said that I'm going to let whoops, that's a typo. I should have called that. I'm going to peek ahead and see what I referred to it. Looks like I referred to it as lowercase a for the rest of this problem. So I'm going to use a lowercase a as I refer to that point. But this is something that in a problem like this one, especially if you skim ahead and look at the problem and see that this point is significant for a lot of stuff, instead of writing down 0.765 or 0.76497 or even more than that, you can just go ahead and label it as some constant. Call it A, call it B, call it K. K doesn't really work for this one given what we're going to see upcoming, but you can go ahead and do that. You don't have to do that, but that's something that you can do, so that when we say the area of this region, well, that's just the integral, top function minus bottom function on the interval between 0 and a, 0.765, top one minus bottom one. And here again, you don't have to tell them that you used your calculator. You don't have to say FNINT. And maybe more importantly, you don't have to anti-differentiate this. You can just go ahead and say this integral is equal to this amount. Now, when I did this calculation, I used more than 3 decimal places. 3 decimal places is what's required for an answer, but you should use all of the decimal places. I didn't even use just this much. I used whatever it was on my calculator when I plugged this into the integral. 0.534, and I don't remember for this one specifically if it was 0.533 rounded up or if it was 0.534 rounded down. Usually on an AP test, they will accept both if you truncate or just chop off after that decimal place, or if you round correctly. I always would recommend rounding correctly, but if the answer was actually 0.5338 something and you called it 0.533, that will get you credit most of the time. Probably all the time, unless they state specifically or something like that. Part B, this is why I didn't want to use K previously. They're saying that I've got this horizontal line, y equals K, and they're basically just asking us if it divides this thing in half. Is the area up here equal to the area down there? Now, there's a few ways of doing this. Because in part A, we found the total area was 0.534, we could just find the area of one of them. And if it's not half of what the total area we got in part A is, we could probably use that to explain that the areas are not equal. I chose when I did this one to say, here's the area of the, let's see, this must be the top region. So my top function is 1 minus x cubed. My bottom function is just y equals k. And here again, when I used that x value that I found in part A, this was the x value, and when I plug it into either one of these two, I get the same y value. That's the value of y, that's the value that the constant k is at that point. And this is all the work you need to do to show that. Do not try to do this algebraically. It will end in nothing but heartache and bloodshed. So stick with writing it down, saying this is solving the equation, this is plugging in, evaluating the expressions, and that's the number that we're using. And since I stated it here, when you're writing out the integral, you don't have to write 0.55235. You can just call that k. That's perfectly acceptable. Anyway, I do both of these. I find the area of the top, I find the area of the bottom. They are not equal to each other. That's what they're asking me to do. So that's all the work I would need to show for part B. In part C, here we go, the volume of a solid of revolution. I don't know that that you're going to have something like this on your AP test. If you were taking an actual full AP test, I could guarantee it. I would guess that this is a significant enough idea that they would put it on there in some context, but who knows? Either way, let's be prepared for it. We're rotating around the horizontal line y equals -3, and not exactly horizontal. And so if this is y equals -3, then when I'm finding my radii, my outside radius and my inside radius, this is pi r squared minus pi r squared. My outside radius is the distance from the axis of revolution to the point on the region that's farthest away. So that's 3 to get up to the x-axis plus the function 1 minus x cubed. There's my outside radius, and then my inside radius is the distance from the axis of revolution. There's the 3 plus the function to the point on the region that is closest. So 3 plus sine of x squared. There is my inside radius. I've already stated in part A, I think I even stated it in part B, the value of A. So I don't need to state that again. I write out the integral, I write down the answer, and that's it. I'm hopefully getting full credit. And I do believe this was another one where the answer on my calculator was actually 11.840 something, and I rounded that one up, but I believe 11.840 is accepted as a correct answer. Reminder to you that the scoring rubrics for these are all included in the PDF, so you can look and see what the points are. For every single free response question, it's 9 total points. And I don't remember, and I don't think I have that file open right now, so I think based on the level of difficulty of these 3 parts, I'm guessing it was 3 parts or 3 points for each part. For this one, probably 1 point for the integrand, the stuff that we're integrating, 1 point for the limits and the constant, and 1 point for the answer. But I guess instead of me guessing at it, if you're curious about stuff like that, go ahead and take a look at the scoring rubric at the end of the giant PDF document that you've been looking at. And then question 3, reminder, skip question 2. It's a good question, but covers stuff that we didn't do involving motion in 2 dimensions. So we'll skip straight to question 3. Let's see, I have a volume of water. W is the volume of water. Notice that we're looking at W prime in here. So this isn't the amount of water, this is the rate that the water is coming in. And as soon as I see that, as soon as I'm looking at a question like this and I see that we are given some form of a rate function, I know that integration is going to come into play at some point. I'm going to have to integrate this rate function to find an amount. But let's see where that shows up. I'm given the rate at a couple different times over a span of 30 days. At time t equals 30, so at the end of this situation, the reservoir contains 125. So we have the amount of water at the end of the situation. Part A, they want us to use a tangent line approximation at time equals 30 to predict the volume of water at time t equals 32, so 2 days after the data that we have. They said specifically to use a tangent line approximation. Honestly, the first thing I did when I did this problem is I just wrote this down. I said that we've got the amount that we have at day 30 plus the rate that it was going up times the amount of time between day 32 and day 30. But then I wasn't sure, because they're saying use the tangent line approximation. I wrote this out also. I'm not sure if this would be required, but this is just my point slope form of a line. Y1 minus, excuse me, y minus y1 equals the slope times x minus x1, except instead of x's and y's, we've got w's and t's. I don't know if you would need this, but I thought it'd be safe to write that down. And then you see that if I go from here to here, I'm just moving that 125 over to the right side, adding 125, and then plugging time equals 32 into the equation. So that is part A. Part B, using a Riemann sum with 3 subintervals. So here's Riemann sums. I think this was a non-calculator question. In fact, I'm pretty sure it was a non-calculator question. I didn't include that when I cut and paste, but I believe that it was. And so I'll keep that in mind as I'm doing this. Let's see. Estimate the volume of water at time equals 0. Okay, so first I evaluate this integral, and so you can imagine the graph of what this would look like. I would have rectangles with heights of 0.6, 0.7, and 1. We're doing a left Riemann sum, so the left side of this interval is a height of 0.6, the left side of this interval is a height of 0.7, and the left side of this interval is a height of 1. The width of the intervals, the width of your rectangles are the change in t-values, so 10 and 12 and 8 are the different lengths, and then I'm just adding up the areas of rectangles, base times height, base times height, base times height. And on a non-calculator part of the assessment, it's going to be things like 10 times 0.6, 1 times 8. The only one that's slightly tricky here is 12 times 0.7, but hopefully in this honors level calculus class, we're able to do things like 12 times 0.7 without a calculator. And then we add those up to get 22.4. Now that's the value of this integral. The next thing they say is use this to approximate how much water was in the reservoir at time equals 0. I'm going to this formula, and I've been emphasizing this as we've been going through the multiple choice questions also. The amount at time equals 0 is the amount at time equals 30 plus the integral of the rate between 30 and 0. Now, if you don't like this, if you want to move this over to the other side and say the amount at time equals 30 equals the amount at time equals 0 plus the integral from 0 to 30, that's okay also. I'm keeping this more general because this is the stuff that I know, and this on the left side, the amount at time equals 0 is what I'm trying to find. I kept it in this form. If the integral from 0 to 30 is 22.4, then the integral from 30 to 0 is negative 22.4. Or you could also just think of it in terms of if the amount at time equals 30 is 125, and the accumulation over those 30 days that we found in the first part of this problem is 22.4, well, then I'm just going to take 125 minus 22.4 to get 102.6 gigaliters. Part C. Explain why there has to be a time other than at time equals 10 such that the rate that the tank is filling is 0.7. So at time equals 10, it's filling at 0.7 gigaliters per day. Why must it be that it happens some other time? And what they're looking for, this is an intermediate value theorem problem. If you want to state the intermediate value theorem, you can certainly do that, or if you want to use that as part of your justification, you wouldn't need to as long as you've got everything that's required for the intermediate value theorem. We do have to say that this is continuous. They told us that it was a twice differentiable function, which means its derivative must be differentiable, which means it must be continuous, and that's what we need to have happen. Basically, I'm looking at the data saying that at time t equals 22, the rate was bigger than 0.7, and at time equals 30, the rate was less than 0.7. So at some time in between there, it has to cross over. If it's continuous, I would guess that we're not going to get credit if we don't say something about it being continuous. And here's the rest of what I was just saying. At this time, it was bigger than 0.7. At this time, it was less than 0.7. So there must be some time in between where the rate is exactly 0.7. And I suppose if I was going to cite the intermediate value theorem, I would probably say right about here, by the intermediate value theorem, there must be a time such that the rate is equal to 0.7. But it would not be required that you state that, but it also wouldn't hurt if you know that that's what you are citing. And finally, part D. Here is an equation, gives a relationship between the area. And when I saw this, I got a little bit scared because I thought they were going to have us do some really fancy, solid of some kind of a density or some weird thing. But then when I read the rest of the question, I saw it's looking for the instantaneous rate of change of A with respect to time. And we're given, we know what the rate of growth of W is. Basically, this is just a related rates problem. And so I've got my equation. They gave me the equation. They told me how A and W are related. They told me how fast W is changing. We know dW dt. So if I take my derivative, I end up with something that looks like this. Again, without a calculator, 0.3 divided by 3, 0.2 times 0.5 divided by 5. These are all things that hopefully we're okay dealing with decimals without a calculator. And honestly, if not, if you just left it like this, you're still going to get credit for it. If you say 0.2 times 0.5 divided by 5, you're still getting credit. I hope we're able to do stuff like this without a calculator, but you wouldn't necessarily need to. Same thing with the cube root of 125. If you don't know the cube root of 125 and you leave that as the cube root of 125, you are still going to get credit for it. Anyway, we plug the information in. We're doing this when the amount of water is 125. The rate that it is changing at time equals 30 is 0.5. We plug all this stuff into it, and I get this amount. 0.02 square kilometers per day is how fast the area is changing. Now, in this one, they said in square kilometers per day, so I don't have to necessarily state this. It may not be worth points. Sometimes they will specify and they will ask for specific units, where if you don't include that, you may not get full credit for a question. So watch out for that. If they ask for the units of measure, be absolutely sure that you are stating the units of measure. Okay, that's the first two questions. We'll take a look at some of the other questions next week. Also next week, some other teachers across the country have been taking guesses as to what this AP test is going to look like. No one really knows because it's brand new for us this year. But people who have been doing this for a long time have been starting to take guesses of what kinds of questions will they be asking. How are we going to sum this year up in one 45-minute test? And so I'll show you a couple examples of that next week, probably either Tuesday or Thursday, and we'll keep moving on from there. As always, if you have any input or suggestions or requests for what we do in preparation for the AP test, certainly let me know. Otherwise, keep answering the little mini quizzes that I've been putting up every day. This information is useful for me, and it's also a way that I can justify giving you some homework points to help some of you raise up your grades a little bit near the end of the school year. So keep doing that. Keep up the good attitude. Hopefully you have a great weekend, and I will see you and talk to you on Monday. Peace out.